Okay, so anyway, I've blown enough time. I just want to remind you of, I always try to review a little bit of what we did last time. And I can blow, sometimes I'll actually almost redo a lecture if I feel like folks are a little bit stuck. But we're still in this ultra easy part of the course. And some of you guys in the back, maybe tell me if you need me to write bigger. If you're having trouble seeing, it's awkward with one board. I'm writing a bit smaller. Just wish I had, see, if I had two boards, I could write a lot bigger because I have more space. If you have trouble seeing, just watch the video. The video seems, I actually enhanced the video a bit because I noticed this could be a bit of a problem. But regardless, I tend to use what I call the VM form of the van der Waals equation in class, and then on the book I use the one where you can see number of moles. Same thing. I did flub that Residual equation. The first time I wrote it down, the second time I wrote it down, I wrote a different form. They're not equivalent, so that was a big screw up on my part. Again, I only use the Residual equation and a real gas equation for homework questions. In class, I tend to stick to the van der Waals. The van der Waals is a little bit easier to understand what the parts mean. Recall that what we did was we applied limits to this equation and found that B is the volume of the molecules. Again, I use a lot of shorthand, obviously, I don't PowerPoint. And A is a little bit less easy to see because B has units of like liters per mole, meters cubed per mole. So that's really easy to understand. A is a little bit more difficult because it has weird units. I don't even remember what they are. Pressure, volume squared per mole squared. Anyway, this is due to attractive forces, which is kind of my analogy was like a galaxy and there's gravity holding it together, some dark matter and dark energy too. But anyway, at night before I go to sleep, I like to put on a YouTube video, and sometimes I watch like Stephen Hawking stuff. Anyway, then I fall asleep, and then I wake up with a cat on my face. And so, yeah, there's not really much more to say about that. And I also recall that the way I did a lot of this was just middle school algebra. I also warned you that I actually covered a lot of the types of material I covered tend to get on the first test. So last lecture was like really important. So is this one. I do take a lot of material on today's lecture, and I tend to put it on the test. Again, to a fault, I tend to teach the test. All right, anyway. Okay, van der Waals equation. Now, it turns out, God, it was like, how many of you engineers again? It's like, oh, God. Yeah, okay, almost all of you. So I think you've already heard of compression factor. Is that right? Have you heard? Wait, have you? Yeah, you heard it? Okay, who's a chemist? Have you heard of compression factors? No, okay, half of you can leave. No, okay, I gotta warn you, you engineers. Okay, look, I don't have a choice about this, but it turns out that some of the conventions in chemistry and chemical engineering are not the same. Like sometimes I'm gonna have a minus sign when you're not used to one. I'm sorry about that. So anyway, please stick around because I may do things slightly differently. Now I also tend to bleed information about what's on the test, so that'll keep you here. Okay, anyway. Okay, that means an aside. That means I'm going in a different direction. And it's for you engineers, I know that this is huge, but there's this thing called a compression factor. You chemists you haven't heard of this before. And I will write it out and talk at the same time because it's awkward not to. A compression factor. A compression factor is a measure of the deviation of perfect gas behavior by a real gas. So it's very simple. Might want to write that down. I can't really write that down. I can express it mathematically. We tend to call it the letter Z. Now what's great about this is that if you're an engineer, and you can imagine you are designing a nuclear power plant, you cannot have anything go wrong. And you probably have pipes of steam, right? Now I've always wondered that, the way a power plant works is that you get really hot steam and you turn a turbine. And I've always wondered why don't you use methanol or something that you don't need as much heat to vaporize. And I think the answer is it's dangerous. Maybe some of you guys know, tell me later. But of course, because especially water is not going to follow PV equals nRT at high temperatures and pressures, you have to know how much off it is. You need to know what the real pressures are given the temperatures and whatnot. And what you can do is find what are called steam tables, which are largely just tables of compression factors for a given set of conditions, which you would then just multiply by P equals nRT to know exactly what you really have, so you don't really kill yourself or everybody else. Now, I want to express this two different ways. The way it's traditionally shown is the pressure, that would be the real gas pressure over P naught. And I think I said this last time, this would be the perfect gas pressure. And, okay, awkward while I write and not talk anyway. It's often expressed this way, so it's just like, okay, P equals nRT, again, high school, versus what is it really? Now, okay, fine and good, so that's a measure of how a real gas is not behaving itself. Now, you may also recall that, based on last lecture, it's often true that the real gas pressure is less than the perfect gas pressure. However, that is not universally true. It depends on what you're thinking of. Because I remember last lecture, I talked about how P minus P naught is usually negative, and that's the A parameter doing that, but I invoked conditions of very low pressure. Well, in a nuclear power plant, those things are at high pressure. So that may or may not be true. So P may not be less than P naught, P may be greater than P naught, Z can be greater than 1. Anyway, so now this is very easy to visualize, but this is the thing I want to kind of push you on a little bit. I'm not going to put this on the test or anything. I just want to point out the complexity that we run into, and there's not always an answer. It looks like I need a new pen. It turns out that I can say that the pressure is wrong. I need a correction factor for the pressure. P equals nRT gives me a pressure that's probably too high. So I'll multiply it by this correction factor. Now I have the real pressure. You could say that the volume is wrong. Right? Now don't write this down, all right, because you already know this, but PV equals nRT. Okay, where do I put the little naught? Right? Which is the real pressure, and which is the pressure the perfect gas pressure, or the volume of the perfect gas pressure? Okay, if this equation doesn't work, now the number of moles I can control, temperature I can always control. That's ridiculous to say I can't control those. But if PV equals nRT doesn't work, which one is wrong? Is it P or V? Both? Not neither. One or the other or both, and all three of those work. So if I put that on the test, those are three answers and they're all correct. And so anyway, my point here, and don't worry about this, I'm not actually going to put that on the test. I just want to point out that this is all nuanced. Like on the homework I said, is the A parameter more important than the B parameter? And really, anything you put is I'm going to count correct because it's a matter of opinion. And oddly enough, this equation is just not all that straightforward. Now, the reason that we tend to put this in terms of pressure is because we make these measurements in rigid containers, like a metal box. So you can't really say that the volume is wrong, right? That doesn't make sense. So we tend to put it this way. However, if I had a balloon, I have steam in a balloon, I could say that the volume is too small. The balloon's a little bit smaller than it should be, and that would be equivalent. You know what, I actually could say, in terms of let's say it wasn't a rigid box, I could say you're putting that gas in a smaller box than it wants to be in. So that actually does work. But anyway, just my point is that this is more nuanced than you realize, but don't worry about it. I'm just pointing it out. This stuff, even P equals nRT, can actually be kind of complex, and that's because there's more than one variable. Anyway, I'm rambling now, so let me mathematically define. I'll probably fix this pin here in a second. See, I like to use the volume for this next part using P equals nRT. It gives us a formula. Okay, remember that's a therefore. Z is Vm P over RT. And therefore, ZRT is equal to PVM. Now, notice there's no little, in case you're getting a little confused about what's what, I don't have, I don't have a little knot, is that right? There's no little knot, right? I got myself confused there. Okay, so again, you can see that Z is just like a correction factor, and that's why you can express it in a giant table. If you Google it, you can find giant tables of Z as a function of like temperature and pressure. A question?
In your V naught, or your V naught sub n equals, that P should be a P naught, right? And then didn't.
Yeah, well, so again, though, it kind of is subjective what's, I think it's actually kind of subjective, right? I don't think I can actually simultaneously have both. Or can I? I haven't really thought about it. I gotta stare at this a little bit more. No, I know I'm okay here. I know I'm okay here. And then so, yeah, tell you what, let's say I go here. Okay, now I shouldn't be doing this because I could very well confuse myself, but so that'd be ZRT over P, and so and that's equal to what? P over P naught. So it looks like I could probably have a knot in one of these, right? That would be okay. Yeah, I have to admit now I've gotten a little bit lost here. Regardless, not a big deal. I've actually kind of thrown myself off where the knots are and where aren't, and actually that's because it's not actually clear. Like, what do you want to say? It's the perfect gas pressure or the perfect gas volume. Anyway, so despite my little bit of flummoxing right now, I will promise I will make this very clear on homeworks and whatnot. And what we're going to do with this, though, let me point out what I'm going to do with this guy right here. So this is the thing you want to put down, is we can manipulate real gas equations. I'll get this figured out. If I'm like way off where my little knots are, I'll actually write you a handout. If you look at the resources section of the book where I have lots of handouts, and I'll try to label those for what chapter. I haven't specified maybe like when you want to look at one of those. By the way, all those handouts came out from when I got confused in class about something, and so I wrote a handout so that I try to minimize the damage. And so that happens a lot, by the way. So I want to point out a couple of things about compression factors, and again, because I don't PowerPoint, I have to draw data in class, but I've, hopefully can do a well enough job of this. And I want to plot this as a function of atmospheres. Atmospheres is a little bit more immediately understandable to a person. Okay, 200 atmospheres. By the way, to calibrate you, one atmosphere is one atmosphere. 2 atmospheres, see, I'm really scared of gas tanks, by the way. It's like I'm scared of electricity and gas tanks because those can kill you quick. 2 atmospheres, that's dangerous. Crappy glass, if you're doing some kind of experiments and you're working with like a really thin test tube, and I don't know how you could, but if you pressurized it to 2 atmospheres, it's likely to blow up. If you go above that, it's going to blow up, and then you're going to have fluoride glass. So my point being, above about 2 atmospheres, objects are becoming dangerous. This is about the limit of what you could ever do with a gas safely. And I happen to know this because I used to do a little high pressure gas research. If you're doing something really dangerous in life, you have to get some kind of permission from the fire department so that they know that you're not just some wahoo working with like really specialized high pressure equipment. So anyway, my point there I'm elaborating is that 200 atmospheres is like insanely dangerous and extremely, it's just insane to handle anything at that kind of high pressure. Okay, so you see that hydrogen is above 1, and I said that's a little unusual. Nitrogen, I like nitrogen because our atmosphere is mostly composed of nitrogen. Methane, because that's basically gasoline. I'll always treat methane, despite the fact it's a gas, I'm always burning methane as examples. When we get to reactions, I'm always using burning methane as an example, because of course that's about the same thing as gas. Okay, the things I want to point out, and I'm going to spend a lot more time on this in a little bit, is that Z can be above 1. Now, it looked like it should be less than 1 based on last lecture, but again, I was using an example of a very low pressure to show you that real gas pressures tend to be less than perfect gas pressures, but it's not always the case. It's also gas dependent, and that means that I'm going to be using the van der Waals, and A and B parameters are going to make all of these different. And the last thing I want to point out to you, now this is a different scale. Let's see, I think this pen will die any minute. I'm not going quite to 0 here. I'm also in atmospheres. It's not going to quite be as high pressure. Now, okay, I'll tell you what. What's a perfect gas? If I drew a perfect gas, what would it be? Yeah, right at 1. Doesn't matter. Okay, let me finish this. I'll get a new pen. Okay, so what I'm going to draw is CO2. CO2 is not, well, greenhouse gas and all that. What's kind of neat is that its behavior is very non-perfect. And what I want to point out here, obviously this is slightly above room temperature. If I lower it to about where we're at now, again, you know, I'm just doing this for, you know, I hope none of you are like thinking like, oh, I need to memorize this stuff. You definitely want to memorize what a compression factor is, but these curves I'm drawing, no, do not memorize them. The lesson here, I'm just using this to illustrate the things I do want you to know, which is that Z, okay, hold on. Hopefully you can see this. Z is temperature dependent. And I will kill the pen with that. And this is one of my backup pens. I'm just actually trying to pull out my backup pens. And all that I then have to do is go to my real pen. Do any of you see it? Because it's disappeared. That's really funny. And what's really great is that I can actually talk while I'm panicking. And so, no, I'm just kidding. It's fine. There we go. Okay, so Z is temperature dependent, and that's why you have to make giant, huge tables of Z versus pressure and temperature. And again, if you're designing a power plant, then you really want to know what your actual pressures and temperatures are. So hopefully this is as boring as watching ice melt. As usual, it'll get a little bit more exciting. I just want to point out some trends. Okay, this is usually much better. Okay, Z greater than 0. Greater than 1. Greater than 1. God, it's always greater than 0. Greater than 1. Okay, I'm going to harp on this a lot. Helium, hydrogen, and what's the lightest Nobel? Neon, I think? Yeah, I think it's neon, right?
Helium.
What's right below helium? That's neon. Yeah, so those are weird gases. Those behave differently than all other gases. And their Z's tend to be greater than 1. And so, now why is that? So let me just write that down. Helium, hydrogen, and again I think neon. I was just Googling that just the other day. And really just those three. Really almost nothing else does this. Maybe, well, nitrogen a little bit if you go very high. Notice that nitrogen, again, is the most perfect of all gases. And notice that, of course, our atmosphere is mostly nitrogen, which is why back in 1800 they zeroed in on P equals nRT. So it's actually kind of a good thing. Let's see. Obviously, these are the lightest of the light, right? These are the ones that melt. If you recall, we looked at the A parameter as a function of melting temperature, and at the bottom, of course, are helium and hydrogen. These are the things that vaporize, they melt and vaporize, all in like 3 Kelvin, 10 Kelvin. So these are obviously very low temperature boiling point gases. Now, if we look at the van der Waals, these are, I'll put it this way, these are dominated by the B parameter, and by that I mean that the A parameter is minimized, its effect is minimized. Often I've seen this expressed, and this is kind of confusing, I've often seen this expressed as A is nothing and B is everything for these gases, but if you look at the actual numbers, that's not quite clear. Van der Waals equation is complicated enough that it's hard to see, but it is true that B tends to dominate the behavior of these gases and A is very minimized. Now, again, remember I was saying the point of this class is to take the empirical fits of the van der Waals equation to those steam tables or whatnot and get A and B parameters and understand things about the molecules. What I understand about helium is that it's a billiard ball. It's very, if I could shrink myself down and hold it, it would be like a billiard ball. So these things are just hitting each other. Remember that B is the thing that allows things to collide. The reason things collide is because they have volume. Things that have no volume, like perfect gases, don't collide, and B does that. Billiard balls aren't going to be particularly attracted to each other, unlike something like xenon or water, which is more like a foosball. Those can get stuck together. So that's how you want to think about that. Okay, now Z less than 1 is for large, and hopefully you remember this. I talked about this last time, polarizable. My spelling is terrible, so I had to sit there and think about it. Large and polarizable. That'd be something like xenon. It turns out that, take xenon with the, I like to use argon, xenon, neon. I like to use those as examples because they're monoatomic, because as we get to more complicated, we get to like water and CO2, the fact that they can rotate and vibrate becomes a bit of an issue, so I like to stick with those examples. What happens is with xenon, the electrons are so spread out, it's such a, if I could shrink myself down, helium barely fits like a golf ball. Xenon would be like this, it'd be kind of like like a giant foosball, right? So those electrons, I can like squish them, I can move them around, I can polarize it, I can kind of give it a squeeze, and maybe it'll start to look like a p orbital. And then it has a dipole, and then it has a dipole, then it's going to have Z less than 1. Let's see. That's all I wanted to say about that. Sometimes I ask like true and false questions based on this stuff, and that's a little bit. I try not to ask questions that are just based on memorization, but I can't do that perfectly. When you see the homeworks are a good guide. First test, you'll figure that out. But I can't do that perfectly, and so sometimes I do have, like, whenever I do ask whether you remember stuff in class, it's something I tend to go for. All right, anyway, so there's not much to be said about that. It turns out that all of this stuff really ought to come out of the van der Waals equation. And again, I always like to use what I call the VM form in class because it's just easier on my wrist. So, see, this is the problem with one board. I've already eliminated my perhaps questionable equation for Z. And what I'm going to do is, when I do operations, I'm going to tell you what the operation is off to the right, because otherwise you might get lost. So I'm going to multiply by VM. Actually, for you guys, I think you're mathematically a little bit more adept. You may notice that I immediately hit Z just by multiplying by VM over RT. Okay, but then I've got to do the algebra in my head. Now remember that on the test and whatnot, most of this, especially this first part of the class, this is middle school algebra, and often calculus. I'll give you calculus identity, so you don't even really need to do the calculus. So anyway, if on the exam, and I universally do this, by the way, I'll give you a real gas equation and say, give me compression factor. I almost guarantee you will see a question just like that. That'll be one of the harder questions. It's all middle school algebra. And remember, if you find that you're getting stuck, if you find you can't do it in 2 or 3 steps, walk away from it, do a different question. Anyway, okay, I'm back. All right, so now the neat thing is, now you recall that B is a small number. You've done your homeworks now. B tends to be like 0.05. A is correspondingly small as well, but what I can see here is that a number over a slightly smaller number is always going to give me a number greater than 1. So now you can see what drives Z above 1. It's exactly what I said, the B parameter, and the B parameter is the thing that makes things collide with each other. Okay, here's another thing. Here's another way to think about it. If I've got this container and I'm pushing on it, and I've got a high B, a B-centered gas like helium and hydrogen, what happens is they start hitting each other all the time. They don't like that. And they're like pushing back on that. So the pressure goes higher than I think it should be. And that's what Z is. Right? Again, that's because they start whacking into each other and they really don't like that. And they're trying to fight that. Okay, anyway. This guy, well, A's are always positive, R's are always positive, T's are always positive, D's are always positive. This is what drives it down. Less than one. Attractive forces. And you can just take my analogy, just take the same thing I just said. Of course, if the molecules are attracted to each other, it's like they want to condense. So remember, if I'm holding a box, and remember that the pressure I feel on the inside is from molecules hitting the wall, like my little phenomenological model on the first or second day. All right, if these things are like trying to condense, then they're not hitting the wall, and I don't feel the same pressure. All right, so that's how that works. It's very, very, very straightforward. The van der Waals equation does a really good job fitting Z for the most part. And in the book, I'm not going to harp on this in class. I don't quite do things exactly the same way as I did in the book, even though I wrote it, because I like to show you different things so that it all kind of connects. Take that, I just got rid of it. God, that was stupid. That graph I had of CO2, okay, so I have to redraw that. That was done with me. The near room temperature one, this is what CO2 looks like. That's the one I just drew. And van der Waals does this. You know, again, it's ultimately kind of a simple van der Waals, and this is the data. So van der Waals is a very simple equation, but I mean, it's such a simple equation, it's actually predicting, it's got a lot of curvature in it. It's kind of neat that it can do that. Now, as I point out in the book, I show you compression factors of, oh God, what was it? I forgot. What did I use in the book? You haven't read it. That's the problem. I forgot. What did I use? Nitrogen?
You used a couple different gases.
I only used two. There's helium was at the bottom, and at the top was, do you remember? I think it was nitrogen. Yeah, I think it was nitrogen because I have good data on that one. So, and I showed in that one that the van der Waals did a really good job fitting that one. But when it came to hydrogen and helium, which again are oddballs and very difficult to fit, I don't actually show you the results from the van der Waals because it was actually terrible. It didn't fit at all, and I thought it was just confusing. So at that point, I used the Residual equation. So anyway, this stuff doesn't actually fit as well as we would like. And yeah, that's really all I've got to say about that. Okay, now there is another example of measuring gas imperfections. Now again, compression factors, those are really important, especially for engineers. You would actually use these things. So for you chemists, if you become engineers, probably not such a bad choice, because you chemists, God, I shouldn't say this, look, I'm a chemist, all right? But you engineers, you know what you're going to make when you get out of here? Money. You know what you chemists are going to make? Kitty food. Sorry, folks, you chemists, you need to go to grad school. Probably you're doing pre-med, right? So you really need to do something. Engineers, good for you. You're going to do pretty well. Get with an oil company, but definitely compression factors are real things that people actually use. And anyway, it's just kind of funny. Engineers definitely make you don't really need to go to grad school. There's definitely less chemists in chemical engineers in chemical engineering grad school than chemists in chemistry grad school, because you don't really need to. I can't blame you for that. I would encourage you all to do it though, because you still make more money, and it's interesting. And do you guys know that you know that you get paid to go to grad school, right? You didn't know that? A lot of, like when I teach 340, almost no one knows that. It's not a lot. You get paid about $26,000 a year. It's about 5 years. But I can tell you, I've actually, since I'm in econ, right, I'm getting MBA, within 2 years, you make it up and then you make more. So anyway, think about that. Glad to write letters for you guys. Anyway, I've gone off the deep end. Only one more thing to talk about is residual volume. Okay, this is like another type of Z. It's another measure of gas, of real gas behavior, of gas imperfections. All right, everyone. So again, a trivia type question on the exam. Name 2 ways to measure gas imperfections. It's actually a question on the 5th problem set. So anyway, I'm actually giving you an answer 5 problem sets from now. Compression factors, residual volumes. Okay, what's a residual volume? And this is more akin to what I was talking about before. which is there's really, let me just write it down. It's just a little formula. And this time, hopefully I won't get flummoxed on where there's a little knot. And I'll figure that out. I'll actually have to watch the video and figure out where I got my knots little knotted up earlier. Okay, so here is what we're doing is we're letting the gas expand. So remember, this is very large volume or low pressure. Those are the same thing. And what I'm going to measure is, and I'd have to do this in a balloon, and I'm going to measure the volume in the balloon and compare that to PV equals nRT. And the little knot will mean PV equals nRT. Okay, so that's fine and good. And that's called a residual volume. Okay, now let me insert the perfect gas law. And then, of course, what we're going to do is try to pick this out of the van der Waals equation. On homeworks, like I'll have you use a virial equation. Sometimes I'll make up an equation of state for you to do something with. So anyway, it bothered me the parentheses were not the same. So there you go. The idea again is that like compression factors, we like to think of this as the pressure's not right. This is an example of like, well, the volumes aren't quite right. And I'll go ahead and give you a hint, because I think I do have this on the next homework. The virial equation is more about residual volumes, whereas the van der Waals equation is more about compression factors. There's a little hint about what's coming up on the next homework. Okay, anyway, so let's do the van der Waals equation, and what we're trying to do is to tease this out of the van der Waals equation. That's the goal, and then we'll apply the limit. All right, anyway, so again, the board is not my friend. Let me always remind you what our starting point is. I actually have this, so don't even look at my notes at this point, but hopefully after 15 years of doing this, I have it memorized. Okay, what am I doing? I'm going to multiply, sorry for the weird use of the board, multiply by Vm minus B. I'm going to multiply by Vm minus B, and divide by P. Okay, so I'm going to do this. I'm going to multiply by Vm minus B and divide by P. Now again, remember on the exam, I have a question just like compression factor, or I'll do this one, and you just have to do some algebraic manipulations. It's kind of like a puzzle question, but there you go. Okay, what have I got? I have to admit I'm a little bit, I have already gotten a little bit confused what the heck I'm doing. Okay, sorry. Vm minus B times P divided by P times P is Vm minus B. Okay, now this is where I always get this a little bit confused. Okay, then I've got RT over P. Oh, yeah, right. So I got RT over P, because the Vm minus B is canceled. Now this is the part I always get confused. I got A, Vm minus B. See, what always confuses me is that I introduce a second term here. And then I've got P, Vm squared is still there. Okay, there we go. Again, it's just algebra. I just really get embarrassed when occasionally I'll screw this up in class because I just get my algebra confused. Okay, now clearly I've just got to do very simple manipulations. Here's the RT over P. So you can see what you're trying to do. You're trying to get Vm minus RT over P. Okay, and that means I've got B on the other side. Here, I'll bring the B over first. And then I'm going to separate the A term. And again, this is where it gets a little confusing because you end up with this, you end up breaking these up into two. Okay. Sorry, I know I'm in the way. I'm trying not to stand in the way. Okay, so there you go. Now, of course, all we have to do is apply the limit, and there you go. Set. Now, this is where it's like, finally it's kind of starting to get a little bit more interesting. Again, I know this is a little high schoolish still at this point. But if pressure goes to, remember, this is the limit of, I already forgot, pressure goes to 0, right? So what's going to happen to this? See, it seems like I have a major problem, right? What am I going to do? I got minus something, of something going to zero. Then oh, great, now I've got plus something of something going above something going to zero, right? Right, something in P is going to zero, that usually blows up. So what's happened? Have I screwed up? Yeah? Not sure what to do, are you? Okay, here's a hint. If pressure's going, how do I make pressure go to zero? Increase the volume, right? Right, so one's going to zero, but one's going to infinity. Now, how did they balance? Did they? Now, this is kind of, it's tricky. P going to zero could dominate over V going to infinity. Remember that L'Hopital's rule stuff from calculus? It's hard to know. It's hard to know which one's going to win, right? So either it'll go to zero or infinity or somewhere in between, right? But that covers all possibilities. Okay, here's how you do this. There's a trick to this. Again, this is where it gets kind of neat. Let's see, what do I want to do? Okay, I want to point out, where am I in my notes? I have to admit I'm a little lost in my notes at this point. Okay. I want to point out something, that this is an empirical observation. So to get you unstuck. Okay, so now I don't have any little knots. So this is real gas data. Real gas data. It turns out that if I take a real gas, and I have no choice but to take a real gas, and I drive the volume up or the pressure down, it turns out that PVM over RT, again, real data, will turn into 1. Okay, but now this is sticky. This is sticky, right? Because, and this is like motivation actually for residual volume. This is kind of inconsistent with what I talked about last time, how at low pressure, that a real gas has, the pressure is a little bit less of a real gas than a perfect gas, and this seems inconsistent with that, right? So, so let's ask this question. Now this is true, not fooling you here. PVM minus RT. Is that equal to 0? Is that equal to 0? See, this is actually the motivation for doing this to begin with. It turns out it's not. You can think of, again, maybe don't write this down. This is just an example. I'm just going to do it off the top of my head. Let's say that F is x plus 5 and G is x plus 3. Okay, and the limit of x goes to infinity, F over G is equal to 1, right? But F minus G is always equal to 2. There you go. It's kind of a neat little math trick. I'll give you another one. It's just like, I don't know, I mean, it's obvious, right? But it still kind of makes you scratch your head a little bit. Here's one maybe you haven't seen. We actually bring this up in 346. It's kind of important. If you average 5 numbers and then square it, you do not get the same thing as if you square each number and then average it. See what I just did? Average the square versus the average of the square. They're not the same. In fact, the average, take the average and then square it, it's always less than the average of each individual and squared. It's always less. Anyway, so you run into these weird math things occasionally. So the conundrum, though, getting back to on task, the conundrum to what do I do with these PVMs, what you do is replace PVM with RT. Okay, so here's the point. It is true that pressure is going to 0 by volume going to infinity, but they happen to balance perfectly by whatever you set the temperature. And you have complete control over the temperature. A person can always set the temperature. You engineers, you're doing a reactor, you can set the temperature. That is not a problem. So that's why I can take this, so this is how I, when I have a problem with the board, this is how I show you where I'm going next. So let me go ahead and apply the limit, because I can't technically make the substitution unless I apply the limit minus RT over P. Okay, so again, this is just a residual volume, is B minus A over RT plus AB over RT, sorry I'm writing too small, RTVM right? So there's a Vm squared. And guess what? That gets killed. That legit gets killed, right? RT is well behaved, but Vm is not. Vm is going to infinity. Okay, so the residual volume of a van der Waals gas is B minus A over RT. And again, what the purpose of this is, it's a measure of gas imperfections, and it's a little bit of trivia, especially when it comes, compression factors are very important. This is a little bit of trivia, but it gives me questions to put on the exam. That's important. And it does show, again, what are important about real gas behavior. The volume of a gas is too big, of a real gas is too big compared to PV equals nRT, because that gas inherently has its own volume. So that makes sense, and that's what the B parameter does. A, again, always a little bit difficult to see what it does, but it also simultaneously fights. It works the other way and tends to try to compress the gas. So there you go. And again, fodder for homework and exam questions, in all honesty. Question?
Never mind, I see your substitution.
There's an extra VM there. Okay, last but not least, I do just have 1 or 2 minutes. I wanted just to show you one other thing, and then we're going to close out chapter 1. There's just one little neat thing about the van der Waals equation. I'll show you. Now, remember, if you've got some homework to give me, just wait till we start heading out the door. And now this is right at the end of chapter 1. I don't tend to make too big a deal of this in this class. But I just want to point out that when you are below, we're going to cover phase transitions shortly. Sorry, P versus V, these are isotherms. When you're above the triple point, and maybe you remember what a triple point is, the van der Waals equation, virial equation, real data, you get a nice P is proportional to 1 over V behavior. But now, if you recall, when we first started talking about real gas behavior, what I said to you was that you start to get curvature that there shouldn't be. V equals nRT. You start to get curvature. What really happens, though, if you go below the triple point, if you go way below the triple point, you start to see really crazy stuff. You start to see, what's crazy about this is, what I see is the pressure, it gives you a little bit of a headache, okay, but look right here. Volume is increasing, but pressure is also increasing. I know it sounds like at first like, well, yeah, sure, they're both increasing. No, if volume increases, pressure is supposed to decrease. Again, volume increasing, pressure decreases, but not according to the van der Waals equation under the right conditions, at the right temperature, pressure, volume, blah, blah, blah. This should not be, and this is no trick, this should not be. You cannot increase the volume of a gas and raise the pressure. Nonsense. You cannot decrease the volume and lower the pressure. Nonsense. Something has gone tragically wrong. Now, in fact, what you can do, and I talk a little bit about this in the book if you're interested, you can actually map out a region of nonsense. There's a little bit more to it than just pressure increasing with volume increasing. There's a little bit more to it, and maybe I'll speak a little bit about that on Friday. But what happens is, if you take one of these temperatures, pressures, and volumes, all right, get one of your reactors, put a gas in there at that temperature, pressure, and volume, look inside of it. What do you see? You already know. You see a liquid. You see a liquid inside of it. In fact, what I've done in your book is I actually map out where this behavior is, again, predicted by a gas equation, and I put it on the phase diagram, and the points actually match the phase diagram relatively well. It's not perfect, but relatively well. So the point of this is, I see your answer. Just one second. The van der Waals equation predicts liquids. It predicts liquids, which is kind of incredible because it's a gas equation. And the answer to its predictions of instability are, well, there's no liquid there to begin with, so of course it's not right. But it's not right because it predicts liquids. Van der Waals won a Nobel Prize exactly for that. So that's why it's special. Anyway, maybe I'll say a little bit more about